We are now recording. Let's get the slideshow on the current slide, and let me get you to remind me. This is where we left off last time, isn't it? Okay, why is it? There it is. We finished 2.2, but had not started 2.3. Is that right? Good deal. All right. Okay, a few announcements first. Finally, I think all of your Blackboard is there and up to date. I was able Thursday to get all your syllabus loaded. If I hadn't loaded it already, the research paper, instructions, my locator card, several files that either I found or students have found and said they found them helpful. I put those there, YouTube videos and that type of thing. I also put all of the PowerPoints out there, so they're there, and I put the link to the YouTube videos that we've been doing. So it should all be there. Now, I think there may be one minor or two minor changes to it. I haven't sat down to work this out yet, but I believe they have decided to pay me an overload since I should teach only 2 classes this summer. I'm teaching 6. I think they finally said, okay, we'll pay them an overload because a lot of my classes are small. That was what had it in doubt. But if I do, then I have to add more office hours in. If I teach an overload, I have to be here more hours. And that's going to be basically on Tuesday, Thursday afternoon because I can't be here many more hours on Monday and Wednesday. I'm already here till after 9 o'clock, and I don't think many students will be coming by for office hours after that. I sure don't want them to, so I'll make that Tuesday, Thursday afternoon. So if I find out they have done that, I will adjust the office hours both on my syllabus and on the locator card. But that's pretty minor, I hope. Okay, any questions for anything we've covered so far? All right, section 2.3 is talking about the basic limit laws, and so far I only see one textbook, but hopefully y'all are able to follow either on the e-book or older books or whatever, other books. But here are your basic limit laws. I don't think my system will blow this one up any, but let me just see. That's not what I want to do. Okay. Yuck. Okay. Okay, I can do it this way. It will make it a little easier to read. Okay, make it a little easier to read. I may hold off and change that. Basic limit laws. Let's suppose that we have two functions, f and g, and the limit for f of x is x approaches c, and the limit of g of x as x approaches c. Both of these limits exist. Okay? Now they both must exist. Okay? Then, if that's true, then the limit of the sum of those two functions does also exist, and its limit is the sum of the limits. Okay? Now that, hopefully, will seem, duh? Well, of course it would. But indeed, you have to establish that. And since Shakina came here, we have just established it. Okay. So I'd marked you here because I was psychic. Knew you were going to get here, but I marked you incorrectly before. Okay. So, if these two functions have limits as x approaches c, then the sum of the function also has a limit, and that limit is the sum of those two limits themselves. The limit of the sum of two functions is the sum of the limit of those two functions if both of those limits exist. Now, constant multiple law for any number k. Now, this is a real number k. I'm not going to get into complex now, though it'll probably still work, but we're not going to do that, so let's leave it to real numbers. Any real number k, if this limit of f of x, x approaches c exists, then the limit as x approaches c of k times that function also exists. no matter how big k might be, several hundred million, the limit still exists, and that limit, as x approaches c of k f of x, just pull the k on the outside, and it's the k times the limit of as x approaches c of f of x, which we know exists to begin with. So there's the constant limit law. Okay, product law, the limit of a product of two functions whose limits both exist as x approaches c. That limit also exists, and the limit of that product function is the product of the limits of those two functions. This is looking pretty obvious, or hopefully it is so far. And next, the quotient law. If the limit of g of x is not equal to 0, here's the only one that comes with a caveat. The limit of g of x cannot equal 0. As long as that's the case, this one could exist as long as it's not 0, then the limit of a quotient does also exist. That's why you see g of x can't be 0, because the limit of that quotient is the quotient of the limits. And if this limit were 0, then that would be undefined. Okay? So there's the fourth of the limit laws. Let's hit the rest of them. These are perhaps a bit more esoteric. Oh, there's only one more, sorry. Okay. I'll go, okay, that's as far as I'll go. Powers and roots. If p and q are both integers, now before, remember, our k was any real number. Now we're limiting p and q to integers, and q not being 0. Then the limit, as x approaches c, of that function f of x, which we know has a limit, but that function is now raised to the p over q power. That limit also exists, and what can we do with that? Okay? Well, you probably have already guessed it. The limit of that would be the limit of the function itself raised to p over q power. Okay? Now, that's true. Okay? That handles it. Now, here's some assumptions that you have to do. Let's assume that the limit of f of x is greater than or equal to 0 if q is even. Now, why is that the case? What does it mean to raise something to the p over q power? What are you really doing there? Say again?
Getting smaller. Smaller?
What is smaller?
You raise it to a fraction.
Well, not necessarily. Okay, what does that mean? It's just raising it to a power. If this were a 1 here, what would that mean? Raising it to the 1 over q power. Are you familiar with that notation? Raising a function or a number or anything to the 1 over q power. Anybody? That would be the qth root of whatever it is that's before that. So something to the 1/2 power is the square root of that thing. To the 1 over 3 power would be the cube root. 1 over 4th power would be the 4th root, 5th root, 6th root, and all. Okay? So, when you put them as a fractional form like this, you first, well, doesn't matter which order, but you're raising this to the pth power, but you're taking the qth root of either that, and by the way, when you have that notation, I'll just give you a little hint here, and I think I'm going to have to adjust my, oh, I can't do it from here. Okay, I'm going to have to shrink this back and do my pen, and now I think I'll go back. Okay. I'll just go on and include the quotient law, even though I don't need it. We've already covered it. Okay. Now, let's just take an entity. We can take the F, okay? Done me. I thought I could write on here. I still can't. All right, let's go back here. What this means is the qth root of f of x to the pth power. Now you can either do it that way, or you can do it this way. The qth root of f of x and the whole thing raised to the pth power. So you can either raise the power inside the radical or raise the power outside the radical. Okay? Either way works, but it's always the qth root of the function raised to the pth power or the qth root of the function, and that's raised to the pth power. Now, most of the time, for calculational purposes, if they've given you some pretty reasonable functions, this is usually easier to calculate. If you can take the qth root of that function, and it's relatively easy to do that first and then raise it to the pth power. If you raise it to the pth power first, you got a bigger thing to take the qth root of. So most of the time, this is the easier calculation to make. Okay? Does that kind of make sense? Okay. Now I'll go back to the Zoom. It won't get all that on there, but I really don't need it. Hopefully you now have a pretty good feel for what that is. Now, my question to you, why does Q have to be even? Oh, okay, I'm sorry. If, say this another way, if this thing is positive and Q is even, okay, why do they put those two together? Any ideas?
If it's even, the number at even, like this, it's going to say a positive.
Okay, you can only take an even root of a positive number. You can take the square root of 4, no sweat. Can you take the square root of negative 4? Not in the real number system. Sweat. Okay, so that's why they put these two together. If this thing is positive or 0, greater than or equal to 0, and Q is even, then you're fine. Okay, as long as, let's see, and that the limit as x approaches c, this is not equal to 0 if p over q is less than 0. Okay, now, yeah, if the exponent is negative, then you're dividing by it. So this thing can't be 0, okay, because you can never divide by 0. So that's why those two sort of caveats are in there. In particular, for n being a positive integer, okay, if n is positive, then this limit is that. Done. No sweat. Okay? And if n is positive, the nth root, I've been saying this right, the limit of the nth root of this thing is equal to the nth root of the limit of those things. But in that one, you have to assume that your f is greater than 0. This limit is greater than 0 anytime this is even. Okay? All right. I think we beat it to death. It's all the same things that held true for integers and whole numbers and real numbers, taking roots and powers. The same things hold true for the limits. You just can't take an even root of a negative number. You can't ever divide by 0. So as long as you got all those things done, then this follows pretty much what you would expect. All right? Now, It said, before proceeding to the examples, we make some useful remarks. At least they think they're useful. Okay. You can extend this. Let's go back here. You can extend these for more than 2. What if you had 3 functions and the limit of all 3 exists, then the limit of the sum of all 3 exists, and it's the sum of the limits. So you can expand this to more than 2. They just say it generically for more than 2. Okay? That's the first. The sum law is a counterpart for the difference. You notice here there is no difference law because it's part of the sum law. If you make that a minus here, that limit also exists, and the limit of the alpha of x minus g of x is the limit of alpha of x minus the limit of g of x. It's just subtraction is adding the negative of the previous, and that still follows. So you don't need a difference law. You did need product and quotient being different, but you didn't need a sum and a difference law. They followed the same. Okay, that's the second thing. Okay? Especially if you consider the constant multiple, what if that number were -1? Then the limit of -1 times alpha of x would be -1 times the limit of alpha of x, and that feeds back into this one, and that's why subtraction still works. Okay. And then they wanted to remind you of the 2 limits we had at the very beginning, and let me write them down here, I think, and see if you remember those. The limit as x approaches c of k is equal to what? Second? K, of course, okay? Now, that works because the k can be pulled on the outside, and it'd be k times the limit of 1. And the limit of 1 as x approaches c is still 1, and k times 1 is k. So yeah, that still works. Okay, how about the next one? The limit as x approaches c of x. What would that equal? C, okay? That means yes in Spanish. No, I'm sorry. Okay, it means C. It yields C. Because as x approaches c, x approaches c, okay? Pretty obvious. Okay. Now, let's go to one more amplification, I guess you would say, is this. Using the last 2, what if the limit as x approaches c of x to the p over q? Yeah, you just plug in the x to c, and that'd be c to the p over q. Now again, c can't be negative if q is even. Okay, you can't do that. And if p over q, that fraction p over q is negative, c can't be 0. So those 2 things still hold, because then that'd be 1 over c over c to the p. Let's see, 1 over c over p over q, and that can't be 0. Okay. Now that we've got those done, let's do some real life problems. Okay, so I'm going to get out of this, I think clear my screen. Okay, it's not clearing, it's still not clearing, there it clears. Okay, let's do example 1. Let's evaluate this. The limit as x approaches 2 of x cubed. What would that give you? Exactly. Look, don't let the laws mess you up. First thing you try, plug it in. Okay? Plug in the 2 for x. 2 cubed is indeed 8. Okay? Nothing strange or new there, hopefully. About the next one, the limit as x approaches 2, they like that, don't they, of x cubed, they seem to like that too, plus 5x plus 7. Say again? 25. How did you get it? 8 plus 10 would be 18, plus 7 is 25, exactly. Plug it in, plug it in. Do you really need to use the limit laws? They enable you to do what we just did. Because the limit law said the limit of a sum is the sum of their limits. So this would be the limit of this, which we already knew to be 8, plus the limit of this, which we know to be 10, plus the limit of that, which we know to be 7. Okay? So you just add them together. But in reality, all you really have to do is just plug them into the original form, and it works. Yes?
So the thing we got before is just basically the theory behind it.
Say again?
So it would just be the theory behind it.
Kinda. That gives you the legitimacy to do what we just did, to plug in. Yeah. Okay? That's a good way to look at it. How about this one? The limit as x approaches 2. I told you they like that, didn't they? Of the square root of, I didn't write the answer. What was the answer to that again? 25, I thought it was. Okay? Now, the limit of the square root of x cubed plus 5x plus 7. Guess what that would be? 5. You got it. Okay? Because the limit laws say if you have an expression raised to a power, the limit of an expression raised to the power is the same as the limit the limit raised to that power, okay, of that expression, of the limit of that expression raised to the power. And that was 25 there, so just plug in 25 here, you get the square root of 5. Or just substitute and you get it. I mean, there's nothing. You can use the limit laws to get there, or you can just plug them in. Okay? Now, you just have to be careful that everything is still legal. So let's look at example 2. Don't know if this is going to take any more, but just in case, any more room, just in case, I'm going to erase it. Anyone need this up any longer? Okay. Example 2, the A one. The limit as t approaches -1, getting away from the easy 2 now, t approaches -1 of t plus 6 over 2t to the 4th. Anyone want to hazard a guess? That is a 6. 5 over 2. Very good. 5 over 2. Okay? Because the limit as t approaches -1 of t plus 6 would be -1 plus 6 would be 5. And t equal -1, -1 to the 4th power to any even power is going to be plus. So that would be plus 1. 2 times 1 is 2. 5/2. Very good. Any questions on that before we move? Now, you see, doing the limit laws take a lot more room. It's the same thing. It's exactly the same thing. Let's do the next one, the limit as t approaches 3 of, make sure I get it right, t to the -1/4 times t plus 5 to the 1/3. That looks fun, doesn't it? Okay. What you reckon that one's going to do? Okay, just a little bit of a reminder, what does it mean to raise something to a negative exponent? 1 over that thing to a positive exponent. So that would be the same as 1 over t to the 1/4. Right? What do we mean by t to the 1/4? Fourth root of t. But now it's in the denominator. That means that since it's an even root, this thing had better be positive. It is. So we can do this, at least the first part. So that the first part would be 1 over, and since they wrote it this way, I'm going to leave it this way, 3 to the 1/4 power, which is the same as the fourth root of 3. Okay? I don't know what that is. I really don't care what it is too much, so I'm going to leave it like that. If you want to get a numerical answer, we will. Okay? What about the next part? Second? Okay, 8 to the 1/3 power, and what does that mean? Okay, did you say the cube root of 8? Okay, I thought that's what you said. Okay. All right. And what is the cube root of 8? 2. Okay. So this would be, okay, this would be times 2. So this would be 2 over, I'm writing it this way just to let you see it another way, the fourth root of 3. Okay. I just assume leave it as 3 to the 1/4, but just to reinforce to you what that means, that's what we've got. Doesn't say they'll always be pretty. This isn't, but that's your answer. Now, if you want to do an estimate of that, does everyone know how to do that on the calculator? There's probably several ways to do it, but it could be 2 over, I still like this better, 2 over 3, but the 3 is raised to the 0.25 power. I would write it that way. And that would give you a numeric answer. That should give you an answer. Do they do it in the book? No, they don't. They leave it like this. 2 over 3 to the 1/4. And frankly, like I said, I sort of like that better. Here's one of the reasons. They started off with fractional exponents. Why not leave it in fractional exponents? Why go to radicals? If the original problem had radicals in it, then I would be tempted to leave the answer in radical form. So I usually try to give my answer in the same form they gave the problem. So that is, I think, the better answer. But I wanted to write it that way just to reinforce to you what t to the 1/4 means, fourth root of 3. Okay, good deal. Any questions on that? Now, I'm going to erase this. Everybody got it? All right, to erase it. Okay. How about this one? The limit as x approaches 0 of f of x times g of x if f of x equal x and g of x is equal to 1 over x, or x to the minus 1. How would you do that? Just give me an approach. Say again. Be what? 8? X. Okay. What? How did you get that? Okay. I heard a 1. Huh? Okay. And what he just said, this is x times 1 over x, and that would be 1. And the limit of 1 as x approaches 0 is? What? Guess what? What were you saying? What's that? Okay, yeah, but after that, right? About the same time he started talking. Yeah, add exponents. That's correct. How you multiply expressions with same base, different exponents. Keep the base, add the exponents. What's wrong with this picture? Say again? Me? Say again? You cannot divide by 0. This thing right here is not defined there. Tricky question, okay? Remember, the product rule only works if both of those limits exist. Limit as x approaches 0 of x, yeah, that exists at 0. But the limit as g of x approaches 0 does not exist, because that's 1 over x, which is 1 over 0. You can't do, ever, okay? So this thing is not defined, does not exist, okay? You can say not defined, if I could write, or does not exist, D and E, okay? Does not exist, okay? You have to always make sure, and the title of this one, that's why I didn't say it out loud, assumptions matter. Your assumptions have to be met. Before you can use the product rule, you have to, product of two limits, you have to make sure both limits exist first. Otherwise, to do the math first makes it look like it's 1. However, you really should plug in first, and then you see, no, I can't do 1 over x. Okay, so be careful with that. Okay, so that's does not exist is how the book writes it. And guess what? That's 2.3. That's all there is, folks. The summary is a relisting of those basic limit laws. Okay? So, preliminary questions here. State the sum and the quotient law. Flip back a page, or 2 pages, and read them. I mean, they're right there. Basically, the sum law, the limit of a sum is the sum of the limits if both of the conditions have limits. Okay, you have to have that there. If the two things being added both have limits as x approaches c or whatever it is, then the limit of the sum is the sum of the limits. How about quotient law? Does that go the same way? Pretty much, but not quite. What's the not quite part of it? Certainly the two functions both have to have limits, right? That's given. Then is the quotient of two functions equal, the limit of a quotient equal to the quotient of the limits. Did I say that right? Yeah. Pretty much, except any time you're dealing with a quotient, guess what? Same as here. That denominator cannot equal 0. So, not only must the limit exist for f and g, let's say we had those two, but also if the limit exists for g and that g, the limit of g is x approaches k, whatever it happens to be, t or whatever it is, c, if that limit is 0, then you can't use the quotient rule, because then you would be dividing by 0. So that's the only thing you have to remember, the quotient rule. Sum law, the product law, as long as two limits exist, you can use it. Quotient law, you can as long as that second limit is not equal to 0, the denominator limit. Okay, number 2. Which of the following is a verbal version of the product law, assuming the limits exist? Okay? The product of two functions has a limit. Well, as long as the limits exist, yeah, the product of the two functions also has a limit. That's the first part of it, but that's not all of it. The second is the limit of the product is the product of the limits. Yes, that's true too. I would say that would probably be the better one of those two. Let's see about C. The product of a limit is the product of functions. No. You can't lose the limit part of it. And D, a limit produces a product of functions. No. Okay. The best answer there is B, but really it's a combination of A and B. So let me, by the way, I did get your names into the my grade book. And by the way, if I come up with something that's different from, you're the only one with a book here. No, you've got a book too. Okay, anything, you got one too. Okay, you only have a chapter at a time or something. Okay, smart move. You're lazy, you don't like to carry more weight than you have to, right? I didn't say that, did I? Okay. Yeah, they count B as the answer. If I say something that's not in your book, I'm using the old edition of Dr. Bryant took home the new edition with him last night. I got to get Dr. Thomas's copy, so we'll each have a copy, because I gave out the others, so he and I were sharing one. But if he's going to take them home, I need them on the mornings before he comes in. So let's go to number 3. Which statement is correct? The quotient law does not hold if the limit of the denominator is 0 or the limit of the numerator is 0. Denominator, so that's the A part, okay? And sure enough, they got it right. So homework exercises here, these are pretty easy by and large. They may throw a few tricks in on you, so watch those, but do any of the odds 1 through 23, okay? Then try 25, then do either 27 or 29, or both if you choose, and then take a look at 31 and 33, see if you can do either or both of those. For further insights and challenges, there's just a couple more. I'll let you decide if you want to go there. Okay? I'm not going to test you on the more complicated parts there, but on the simple ones. Any questions? Okay. Let's move on to, let's see. Wait, wrong answer. Okay. I've got to get out of this one and go to 2.4. PowerPoint has been a little slow today, so relax and enjoy the music in the background. No, I'm sorry, there is no music in the background. Okay. While this is loading, it'll get there one of these days, I hope. This is a lot bigger file than the last one, and actually it's loading faster than the last one did, so I can't figure. It'll open in a minute. Any questions so far? All right. Do the slideshow from the current slide. There it is. Now, let me first find out, is this what your book has is 2.4? Because they do change around some of these sections in the new edition. Is this what you got? Okay, good. I thought it was, but I want to make sure. Okay, what we're talking about now is limits and continuity. All right. I think we've already been using the term continuity some. In everyday speech, the word continuity means having no breaks, no interruptions In calculus, continuity is used to describe functions whose graphs have no breaks, and I'm going to put this other, no holes. Okay. If this function here were defined everywhere along this curve except there, and it had a hole there, that would not be a continuous function. If it was defined everywhere here, but at that point C, it was defined here or anywhere other than that, then that's not a continuous function. And certainly if it was defined here, but then down here it went to there, that obviously is not a continuous function either. So we'll see some other examples of this. I probably should have blown this up first. I forgot. But after what happened then, well, that wasn't a bomb. Okay. If we imagine the graph of function f as a wavy metal wire, then f is continuous if the graph consists of a single piece of wire as shown here. Everywhere along there is connected. If there was a break in the wire, like this, that is not a continuous function. Okay, not one strand of wire. It's two pieces of wire. Now, even if this were to come down here, but you had a hole there, that's still two pieces of wire. If there's a hole there, if it's cut there, that's two pieces of wire, it's not one. So you have to have, okay, don't want to get too far ahead. That's a discontinuity at C. The left-hand and right-hand limits as x approaches C are not equal. Okay? As x approaches C here, this is approaching G of C. As x approaches C from the right-hand side, you're approaching some number up here. That's not the same as this number down here, so it's not continuous. Okay. Now, here's our definition for continuity at a point. Okay? Now, assume that f of x is defined on an open interval. Now, what we mean by open intervals, everything inside, not necessarily the endpoints. An open interval containing x equals c. So c is not an endpoint, it's inside that. Okay? So assume that f is defined on that open interval containing x equals c. Now, all it says here is f of x is defined. Then f is continuous at x equals c if the limit of f of x as x approaches c from the left and from the right are both f of c. That's your definition of continuity. And this would be true for every c in that interval, open interval. If the limit does not exist, or if the limit exists but is not equal to f of c, then we say f has a discontinuity or is discontinuous at x equals c. Okay? And we'll show some examples of that. Okay? Here's a pretty simple one. Well, hit the wrong button. Okay, there it is. All right. What would you call this function that's represented by the reddish or pinkish line? Say again?
Would it be infinity on the y-axis or the x-axis?
Okay, would it be a what? A B?
Infinity.
A what? I can't hear. My hearing's bad.
Infinity.
Okay, no, there's no infinity here. We're going to assume that the limit is infinity because we don't show anything else. But what this would be, that would be called a constant function. No matter what x you put in there, the y value is always k, a constant k. It's called the constant function, horizontal line. Now, at every c, x equals c, that function is equal to k. Every one of them. So would that be continuous or not? I All right. Good to see you. Okay. Jasmine, right? Okay. And you still go by Jasmine, right? Okay. Beginning to worry. Okay. All right. Do you have a book yet? Okay. We started in chapter 2 and now we're up to 2.4. That's where we're working today. And as you know from Trig class, I've recorded everything on Screencast-O-Matic. It's been saved to, or sent to YouTube. The Blackboard is set up. The syllabus is there. The research paper instructions are there. My locator card is there. I may have to change my office hours some because I think they're going to pay me an overload, so I have to extend my office hours some. Sites that either I found or other students have found and found helpful, I put those there, like YouTube videos and things like that. Other people have done. I've got all the PowerPoints there, and just understand this about the PowerPoint. When you get the book, could you show them the cover of your book, please? Yeah. Oh, no, you have a different one. Okay, that one. If you get the book that's in the bookstore, that one, okay, the PowerPoints are from the older edition because they didn't send me a disc for the new edition. So I'll try to make note of that when I see changes, okay. So far we haven't had any, I don't think. I can't recall any. And so the PowerPoints are out there, but there will be some minor corrections to those. Also, I put the link for the playlist in YouTube, so it's out there too. So everything's there for your viewing enjoyment. Okay. All right. And we're just talking about this function. This function is a constant function. It's constant everywhere, or at least it's indicated as so. Certainly at the point C, the value is k, just like it is everywhere else. So the limit as x approaches C from the left and from the right is k. Okay? So that is a continuous function. The constant functions generally are continuous functions. All right. I'm sorry, that was example 1A. Sorry about that. I try always look and make sure the slide is not getting ahead, but it did in this case. So F, okay, I've got to shrink back, and I've got to get my pen back. Okay, so example 1A, f of x is equal to k. That's a constant function, and as long as k is any constant, we'll call them real constants now, then that's a continuous function. The b is g of x is equal to x to the n, where n is a whole number. Now, just to make sure everybody understands, what do we mean by whole numbers? What does a set of whole numbers include? All your counting numbers, or natural numbers, 1, 2, 3, 4, 5, 6, and 0. So far, no negatives. That would be integers, okay? So whole numbers is 0, and all the counting numbers up. So all the non-negative integers, that's your whole numbers. Okay? Now, as long as that's the case, is that typically a continuous function? Let's just take a few. What if the n was equal to 0? That's the smallest whole number you could have. What would that function be? What's x to the 0th power? 1. Anything to the 0th power is 1, except 0 to the 0th power is not defined. Any number other than 0 raised to the 0th power is always 1. Any expression, as long as that's not equal to 0, raised to the 0th power is 1. So that would be a constant function again, only now the constant would be 1. So we know that's a continuous function. How about if n is equal to 1? What would we call that? Say that again. Y would be the same thing. F of x would be the same thing. We call that the identity function. Okay, it splits us both the first and the third quadrants with a 45-degree line. With x equals c, y is equal to c. X equals c, y is equal to c. That's the identity function. How about if n is equal to 2? Say again.
It will still be continuous.
It would still be a continuous function. That would be a parabola with whose vertex is 0, 0. X equals 3, that would be your basic cubic function. X equals 4 looks a lot like a parabola. It's just flatter here and steeper there. And they go on and on and on. Those are your power functions. Your power functions are continuous functions. Very good. Okay? They don't show all those, but they do show that when n is equal to 1, and that we call the identity function, and that's also certainly a continuous function. X is equal to c, g of x is equal to c, or y is equal to c. Okay. I think I've mentioned this before. One of the biggest things to remember here, if you had, can't remember if any of you had me for pre-calculus algebra, but if you did, I told you then that that's the algebra function. Remember this: f of x is equal to y. Okay. If you don't remember anything, in this case, g of x is equal to y. Whatever your function is, that's what goes in the y-axis. So if you remember that, you're going to be ahead of the game. All right, so let's look at some discontinuities. To understand continuity better, let's consider ways which a function can fail to be continuous. Okay? Keep in mind that continuity at a point C requires more than just the existence of a limit. 3 conditions must hold. And they don't have these on a slide, and since some of you don't have books, I'm going to write these down. So let me do this. Here's the 3 things. Number 1, f of c must be defined. Okay? If f of c is not defined, like if it's going to infinity or something like that, that can't be a continuous function. So f of c must be defined. Secondly, the limit as x approaches c of f of x has to exist. Okay, that limit must exist. Okay? But the third part is these have to be equal. Okay? If the limit exists, it must be that value. Okay? They must be equal. Okay, so there's the third part there. So not only does f of c must be defined, and the limit must exist, but that limit must be what the f of c is defined as. Now, that seems, what are you talking about? Aren't they always? No, they're not. Okay? And here is a classic example of where it's not. This function is here's a function. The pink line is a function here. Okay? However, it has a hole in the function at x equal 2. Now, it has a value at x equal 2 up here at 10. Okay? Now, the first part of this is that f of c is defined. F of this value is defined, that and that and that, all these are defined, and f of 2 is defined up here. F of more than 2 is defined here. All your f of c is defined everywhere, including x equal 2. The limit as f approaches 2 from the left is 5, from the right is 5. So the limit exists at x equal 2, right? But they're not the same value. The limit exists, the function, the value exists, but this doesn't equal the limit. If you move this down to here, now you have a continuous function. So therefore, sorry, I should have blown this up. Okay. This is not a continuous function, that one is. Because all it took was redefining one point, or a finite number of points, we call this a removable discontinuity. It is discontinuous, but by making one major change, it can be removed. Okay? That's a removable discontinuity. So, discontinuities can exist. This one is called a removable one. You change that value from 10 to 5, that is a continuous function. So removable discontinuity, the discontinuity can be removed by redefining your f of 2. From 10 to 5, now the limit is equal to the value of the function. Okay? Up here, the limit from the left and right was 5, the value was 10. That's a discontinuous function. Okay, now, here's another type of discontinuity. Okay? This is called a jump discontinuity. In this case, the limit from the left and the limit from the right are different values. There's no way you can define at x equal 2 to bring those two together. Halfway in between is not going to work because still the limit here would be whatever this value is. The limit here would be that value. Even if you redefine here, they're still not equal to each other. They can't be. So this is a jump discontinuity. It's left continuous at x equal 2. It's right continuous at f equal 2, x equal 2, but those two are not the same. Okay? Now, I said something wrong. This is left continuous there because its limit as x approaches 2 from the left is the same as the value at x equal 2. It's not right continuous at f. It's continuous at it has a limit as x approaches 2, but that limit is not the value of its thing. And you can't redefine this one without losing that. Okay. This is neither left continuous because it has a limit as x approaches 2 from the left. That's that value. But its value at x equal 2 is up here. So it's not left continuous, it's not right continuous, because from the right, it has a limit here, but this value is here. So x equal, f of 2 is not equal to either of those limits, so this is neither left or right continuous at x equal 2. Those are two examples of jump discontinuity. There's no way you can bring those two together, not with them defined this way. So those are jump discontinuities. All right. Now, they've already been hinting at it. Now they're going to give a definition here that defines it, and that is one-sided continuity. That example, or at least the A one there, showed one-sided discontinuity. A function f is called left continuous at x equals c if the limit as f of x approaching c from the left is equal to f of c. In other words, if that endpoint there is equal to that, that is a left continuous function. Its right continuous is as x approaches c. The limit as x approaches c of f of x is equal to f of c. In other words, if that one's colored in, that is a right continuous function. Okay? And this is the way we describe it. The limit as x approaches c from the negative side and from the positive side. Okay? And if these are equal to x alpha c at that endpoint, then, and the limit is there, then indeed that's the, those are left and right continuous. Okay. However, if those two are not the same, it's a jump discontinuity. And by the way, if they're not the same, both of these can't be equal. Okay? Then it wouldn't be a function, because this would have two different values at x equals c. One that's up here and one that's down here. That then wouldn't be a function. So at most, only one of them can be defined. Okay. Now, this, I think, is example 2. Well, forget that. Okay. Here is a function. And for some reason, they made it capital F. F of x is equal to, it's a piecewise defined function. X, for all x less than 1. 3 for x between 1 is less than or equal to x, and that's less than or equal to 3. And then it's x again for x greater than 3. Okay? Now, if they hadn't already given it to you, first thing I'd do is say, describe that function to me. And here's what it is. It's your identity function anytime x is less than 1. That goes from negative infinity, and they don't put a limit there, negative infinity, up to here, but not counting 1. That's why you have to put a circle there. Now we'll lose the written, but so you can see this a little cleaner. Get this in. Okay. So from x less than 1, it's the identity function, but less than, not including 1, that was just less than, you have to put an open circle there. Between 1 and 3, including 1 and 3, that's why you had equal to on both of those, then you have this equal to 3. Then, past 3, any x greater than 3, it continues the identity function. So it continues that function on like this. Okay. Is this portion left continuous? No. Is it right continuous? No. Well, right continuous. How about this portion? Left continuous at x equal 1, right continuous at x equal 3. Okay? How about this portion? Is it left continuous at x equal 3? Yes, it is. Even though it wasn't defined for that, it's still continuous there because by the previous one it was defined there, and it's right continuous. So yes, it is defined as. So this is continuous from 1, including 1, all the way to the positive infinity. Now, it's not a smooth function, but it is a continuous function. There's no gaps, no thing. This is a jump discontinuity. No way you can get those to match or to equal. Okay? It's a piecewise defined function. Some piecewise defined functions can be continuous. Others will have one gap or two gaps, or as many different pieces you have. You could have an infinite number of gaps. So this is one, and let's see what they say about it. It's x equal 1. The one side of the limit exists, but they're not equal. So it's a jump discontinuity. And at x equal 3, the one-sided limits exist, and they are equal, so it's continuous at x equal 3. Okay. So we have removable discontinuities. We have jump discontinuities. Here's a third kind of discontinuity. Okay? And this is called an infinite discontinuity. Let's see if I can get, I think I can get all three of these in one slide. Let's see if I can. Just barely. Okay. These are three different examples of infinite discontinuities at x equals 2. As x approaches 2 from the left, it's going to positive infinity. From the right, it's going to positive infinity. So then can you conclude, since they're both going to the same place, this is continuous? No. Infinity is not a number. Infinity means it just keeps increasing without bound. So ne'er the twain do meet. They get closer and closer and closer and closer together, but you keep going and they keep going too. Okay. The closer you get to 2, the higher it is, but never are they equal. Okay? Because infinity is not a number. Well, this one obviously not. This one, as x approaches 2 from the left, it's going to negative infinity. As it's going to approach from the right, it's positive infinity. Unless you're on a globe where that's going to match up somewhere on the other side, no, and they don't. That's an infinite discontinuity. Now, here's another. This is a bizarre one. This is not going to infinity here. It's going to a value here. But this one is not. So this is left continuous at x equal 2, but right discontinuous because it's infinite. It's going to infinity. So as x approaches 2. So this is also an infinite discontinuity at x equals 2. Even though one of those has a limit, the other does not. It goes to infinity. In other words, infinity means there is no limit. So think of that. An infinite discontinuity, if it's going to infinity, it has no limit. Whether they both go into positive infinity, they neither one have a limit, so they can't be equal to the same thing. Okay? Now, removal of the discontinuity, just changing a value or some finite number of values, make it continuous. Jump discontinuity, no way you can ever make them. The left-hand limit's right-hand limit's not the same. Okay? Infinite discontinuity, either one or both is going to either a positive or negative infinity, means they're increasing or decreasing without bound, so therefore that's an infinite discontinuity. 1 or 2. Okay? There is one more, and that's none. Okay? I think they're going to get to it, but they're going to do theorem 1 first. Okay? So let's do theorem 1, and then we'll come back and hit that last type of discontinuity. Okay? Basic laws of continuity. f of x, and g of x are continuous at some value x equals c. Then the following functions are also continuous at x equals c. Okay? Now this almost sounds like your limits, doesn't it? But this is continuity, not limits. So if f of x and g of x are both continuous at x equals c, then the sum of the two functions are continuous there. The difference of the two functions are continuous there. K times a function is continuous there. The product is continuous there. And the quotient is continuous there as long as that denominator is not equal to 0. So g of c is not equal to 0. G of c is equal to 0, you're going to have an infinite discontinuity there. But as long as g of x is not 0, positive, negative fraction decimal, as long as it's not 0, that is also a continuous function. So again, sums and difference, products, constant multiples, or quotients as long as the denominator is not 0. If each of them are continuous, then their sums, their differences, their products, constant multiples are always, and quotients are always as long as the denominator is not 0. Okay. This is the other kind. They actually said this in the text first, but they on the slide set they had it in a different order, so let's hit it here. They love this crazy example, this function is not defined. Sine is defined everywhere, but 1 over x is not defined anywhere. Okay, wait, I'm sorry. It's not defined as x is approaching 0. You can't do it. You cannot let x approach 0, so therefore no matter what function you're dealing with, it's going to screw it up, okay? And indeed it does. As x gets closer and closer to 0, sine goes faster and faster and faster, up and down, between plus and minus 1, but never reaches some limit. This discontinuity, x equals 0, is not a jump discontinuity, not a removal discontinuity, not an infinite discontinuity. It's a none of the above. It's just discontinuous because the argument of the sign is an infinite function as x goes close to 0. So that would be a neither. Okay? Well, they don't really give it a name here. It's not a jump, removal, or infinite. Okay. All right. All right, they do in the text, if those of you who have the text, they do have a little bit of a proof for the sum part of this basic law. I don't think they do any but the sum, but they do that, and you're certainly welcome to look at that. Now, okay, hate to do this, but I need to take a very quick break. If anyone else needs a break, please take it. Let's keep it as short as possible. So I'm going, hit the wrong key. I want to pause. Hopefully in just a couple minutes you'll be able to see the slide. And we hit the slide, hopefully adequately. This is a discontinuity, but it's not a removable, it's not a jump, and it's not an infinite. Okay? It's brought about by the inner part of it being infinite, but the discontinuity itself is not infinite. Okay. That leads then to Theorem 2. That doesn't, but the book again goes to Theorem 2. All right. If you remember, I'm assuming that you had pre-calculus algebra somewhere, either in high school or earlier at college. And when you were talking about functions, one of the first types of functions you looked at were polynomial functions. And there were two characteristics of polynomial functions. I don't know if your instructor harped on them, but I know I always do in my classes. Two features of a polynomial function. First, not first and second, but they're smooth and continuous. Okay? So right there, I said they're continuous. Okay? So continuity of polynomial functions, they're always continuous. So let's let P and Q be polynomial functions. P of x and Q of x are polynomial functions. Then P of x is continuous anytime you put a real number in it. For all real numbers, P of x, every polynomial function is always continuous. Now, another type of function you looked at was a rational function. What's the definition of a rational function? Anyone remember? First 5 letters of rational. Ratio. What does a ratio mean? Division. One number compared to another in a division sense. So if you're dividing two, and guess what the two functions are going to be? Polynomial functions. So P of x and Q of x are both polynomial functions. Then the ratio of those polynomial functions, P of x to Q of x, that ratio, P of x divided by Q of x, is also continued on its domain. they snuck something in on you. What is the domain of a rational function? Everywhere that the denominator is not equal to 0. All the values x equals c, as long as q of c, the denominator is not equal to 0. Now, there was one other little snuck in part of the definition of a rational function. They don't say it here, but I think it's implied that P and Q have no common factors. I know in our pre-calculus text, not written by this author, but not even this publisher, they threw that in too, that P of X and Q of X have no common factors. If they have a common factor, then you have one of those removable discontinuities, okay? Because if you can divide out x plus 2 here and here, then x equal negative 2 and x equal negative 2 will make the 0 in the denominator, but it can be replaced because you can divide those out. But if they have no common factors, if there's a place where this q of x is equal to 0, q of c is equal to 0, then at that point you have what they call a vertical asymptote. So any time that you have q of c is equal to 0, you're either going to have a removable discontinuity if that results from a common factor, or it's going to be a vertical asymptote, meaning going to infinity one direction or the other. Okay? In fact, usually both sides. So this is continuous on the domain because you exclude from the domain all values that make the denominator equal to 0. All right, but everywhere else, guaranteed to be continuous. Okay? Any questions on that? Okay. They do give a little bit of an example here. I'm not going to do the first one. We've already said polynomial functions are continuous everywhere, all real numbers. Here is a g of x, which is a rational function. G of x is equal to x plus 3 over x squared minus 1. Okay? What can you tell me about g of x? Is it continuous everywhere? Yes or no answer. Okay? Is it continuous everywhere? Okay. Why? There are two places it's not continuous. Where? What kind of function is it? Is that a polynomial function? No. It has an x in the denominator. That can't be a polynomial function. Okay? So what kind is it? A rational function. And what is the limitation on a rational function? The denominator cannot be 0. Can that denominator ever be 0? What is your denominator? X squared minus 1. That cannot equal to 0. How would you solve that inequality? Just like you solve an equation. What would you do first? Anytime you have an expression whose order 2 or higher, first thing you try to do is what? Did I tell you my in mathematics, what's the F word? Factor. Okay, very good. What will you do to the left-hand side? Factor. Is it factorable? Yes. What would it factor as? X minus 1. times x plus 1. Now, is that product? What values would make that product equal to 0? To make this statement true that it can't be 0, that means x minus 1 cannot equal 0, and, not or, x plus 1 cannot equal 0. If that was an equation there, we'd put an or in there. With it not equal to, you have to put an and there. Both of these will make it not true. Okay? So this means x cannot equal 1, and x cannot equal negative 1. So those are the two things you exclude from the domain. Once you exclude them from the domain, then that's continuous everywhere on the domain. But those two are not on the domain. So what does that mean? What does that mean? If you were to graph this thing, you would have a vertical asymptote at x equal minus 1, another at x equal 1. Anywhere on this side, continuous. Anywhere in between, continuous. Anywhere on the outside, continuous. But not at those values there. It's going, that's an infinite discontinuity at those two asymptotes. Because neither of those is equal to x plus 3. Okay, if that had been an x plus 1 in the numerator, then you would have had a removable discontinuity. It would be a discontinuity, but it would be removable because you could factor out the x plus 1s and just have 1 over x minus 1. So x equal negative 1 would be, x equal 1 would be infinite discontinuity, and the other would be removable. Okay. But this one, no, is continuous everywhere outside those values. Now, what if that had been a plus there? Is that continuous? Yes, because there's no place that denominator can ever equal 0. Because the smallest x you can put in there is x equals 0. 0 squared is 0, plus 1 is 1. Positive number, not 0. Any other value you put in for x, negative. Most negative number in the world, you square it, it becomes positive. Add 1 to it, it's even more positive. So that one is continuous everywhere because the domain has no, the denominator has no zeros in the real number system. The original one, it had two places where you had infinite discontinuities. Okay. The other way in the book actually expresses it this way: x cannot equal plus or minus 1. You can write it that way, just remember that's two different values. Okay. Now, let's look at some more functions. Okay, polynomial functions, rational functions. We know what those are. In algebra, what kind of functions did you deal with next, besides polynomial and rational functions? Okay, I'll give you some hint. Some other basic functions. Okay. Okay. First of these are your root functions. Okay. If this is a power function, those are all polynomials. X to the n, where n is any energy. Okay, positive energy. That would just be a polynomial function. But x to the 1 over n, that is a root function. It's continuous, again, on its domain. Okay? Boy, they sneak that in there, and that sort of limits you. For n, a natural number. So n can't be a whole number now, because whole numbers include the number 0. You can't do 1 over 0 up here. So you have to exclude 0. So now we're dealing with only natural numbers, which are also called your counting numbers. 1, 2, 3, 4, 5, 6, 7. So as long as n is any one of those, this is continuous on the domain of that. Always. Now, what you have to remember about this, if this n is two cases for natural numbers. N could either be your counting numbers, or two types of counting numbers you have. Even and odd. Okay? If that N is even, what does the X have to be? Does it mean to do 1 over N? Say again? Yeah, if N is even, X has to be positive. Cannot ever be negative. Okay? It could be 0, but it can't be negative. If N is odd, doesn't matter. It can be all real numbers. That's why they say on its domain. For N and natural numbers, if N is an even number, then the domain of this function is greater than or equal to 0. If N is an odd natural number, X would be all real numbers. Okay, let's look at the trig functions. At least 2 of the trig functions. How about sine and cosine? Continuity is what we're talking about. They're continuous everywhere. They just do this and this and this and this and this. Forever and ever and ever and ever and ever. In both directions, they're always continuous everywhere. All real numbers. So sine x and cosine x are continuous everywhere. How about tangent? Say again?
It's also continuous.
I can't hear.
Tangent is also continuous.
Tangent is what?
Also continuous.
Is it?
Yes.
Okay. Think about how a tangent works. Well, okay. First, tell me how tangent is defined, especially in terms of sines and cosines. Okay.
Sine over x.
Sine over cosine. That's tangent, right? Can cosine ever be 0? Sure it can. Cosine is 0 twice a period. Okay? It's 0 at the half pies. All of your half pies. So therefore a tangent is not defined at the half pies. Tangent is infinite vertical asymptotes to every half pi. Negative pi has, positive pi has, 3 has pi, 5 has pi, 7 has pi, negative 3 has pi. Yeah. All places where cosine is 0, tangent is not continuous. Now, it's continuous on its domain because at the half pies is not, they're not part of the domain. So they're continuous. The rest of the trig functions are continuous on their domain. And guess what? Every one of the next 4, tangent, cotangent, secant, and cosecant, are all defined with one of these in the denominator. So they're continuous on their domains, but their domains are not all real numbers. Their domains exclude certain values. Sine and cosine exclude no values. This is called what kind of function? B to the x. Your variable is your exponent. So this is an exponential function. Exponential functions are continuous everywhere. Okay? If B is, B is always positive, by the way. Never negative, never 0. And the B looks like this for basically that's what your exponential function looks like. Continuous all over the number line. How about a log function? Log functions are not defined x equals 0 and not defined for x equals, and by the way, I said b was always greater than 0. I said that here. I left off b cannot equal 1. B is equal to 1, 1 to any power. Any power is 1. That's a constant function, so that's not really interesting. Okay, so we let b be only positive numbers, but not 1. Same thing here. Log base b of x is continuous everywhere the x is greater than 0. This is continuous everywhere, and this is continuous everywhere that x is greater than 0. Logs are never defined for either 0 or negative numbers, ever. And one of the reasons for that is they're the inverse functions of an exponential function. And if your exponential function, I kind of described it to you, looks like this. By the way, exponential function, x equals 0, b to the x is always 1. So that's what your exponential function looks like, basically, something like that. So therefore, your inverse function would look like this. This would be at 1, 0. I don't have it to scale. So therefore, it can never equal 0 or be less than 0. Because your exponential function can't have negative values. They're inverse functions of each other. Okay. So I think we beat that one to death. However, let's take a look at some of those. Your root functions basically look like the first one. Square root of x, fourth root of x would just be steeper here and flatten out more there. Okay. Your cube root of x would, see if I can get this right. They would come in like this, okay, including negative numbers. But as long as this is even, you're only talking about positive values, not negative values. So it looks like this. Oh, here's the cube root function. Wave my hand, there it is. If this is even, your denominator is even of your radical of your exponent, then you're only defined for x greater than or equal to 0, and they look like this. The larger this is, the steeper it is here, flatter it is up there. That denominator of your exponent is odd, then it's defined for all real numbers. Okay? If it's a 5, be flatter here, steeper here, flatter here. Okay? Your sine function looks just like that. You want to tell me what the cosine function looks like? By the way, continuous everywhere on its domain, which means greater than or equal to 0. Continuous everywhere, continuous everywhere. They didn't draw it here, but it's just continuous. Do it like that. Anyone want to tell me what the cosine function looks like? Okay, Jasmine, you better be able to tell me. You're in my tree class, okay? What does cosine look like?
I was busy writing.
Huh?
I was busy writing.
I can't do it.
I was busy writing.
Oh, sorry, okay. What it looks like is just take this and shift it here. It starts at 1 and goes to 0, and from there on it looks just like the sine. Okay, it's just shifted. Continuous everywhere. And this is what it looks like. No, it isn't. This is your exponential function. And I've already drawn that. That's what it looks like. 2 to the x, when x equals 0, this is 1. Okay? So it always goes to 0 to 1, and there's your exponential function. Now, what they didn't show is your log function. The log function looks just like this, except it's reflected across the identity function here. Now, this is not to scale. There's 3 here, there's 8 there. So obviously they compressed the y scale, expanded the x scale. So your identity function would be something like this, and then your log function, log base 2, would be like this. I can't do it here. I'm going to have to. The log base 2 would be like this. Yeah. Oh, yeah. So it also is continuous on its domain. It's just that its domain does not include any negative numbers or 0. Okay. Now, what I was asking you before was the trig function here's how the graph of the trig function looks. Because a trig function, a tangent function, not trig function. A tangent function is sine over cosine. Everywhere the cosine is 0, you have a vertical asymptote. And that is at your half pies. Every half pi, positive or negative, you would have vertical asymptote there. And it goes to infinity as it's approaching that from one side. It goes to the opposite infinity approaching to the other. That's what your tangent function looks like. So it's continuous everywhere on its domain. It's just that its domain does not include any of the half pies. Does that make sense? And cotangent, by the way, you both have a shift and a change of direction, but it does, well, I can't draw it there. It does something like this. The cotangent is vertical asymptotes of the whole pies, okay? And it goes in the opposite direction. Your secant, on the other hand, looks a lot like the tangent. It starts at, has vertical asymptotes at the half pies, but then it does that. So mine not very even there. The cosecant acts a lot like the cotangent. It's or like this then. If I can get them in the right place here. Yeah, like that. And like this. That would be the cosecant. But don't worry that. The point being, they're continuous everywhere in their domain. It's just their domains do not include certain points. For tangent and cotangent, tangent and secant, the half pies, cotangent and cosecant, the whole pies. Those are excluded from the domain. Okay. All right. Now, continuity of the inverse function. What do we mean by an inverse function anyway? What functions have inverses? What is required of a function for it to have an inverse? Does this mean anything to you? One-to-one functions, excellent. Okay, yes, you got it right. One-to-one functions are the only functions that have inverses. What do we mean by one-to-one function? Okay, let's go back to functions in general. What is true of the graph of any function? It passes the vertical line test, otherwise it's not a function. That's why, remember I said if these two discontinuous functions were both defined, then that's not a function. One of them can be defined, the other has to be a circle. This can be defined, that has to be a circle. Because you can't have two different values for the same input. You can't have two different values for an output. In other words, it has to pass the vertical line test. So guess what a one-to-one function has to do? It's a function, so it has to pass the vertical line test, but what else must it do? Okay, now you're really onto something there, or close to it anyway. It also has to pass a horizontal line test. So, I don't know if this is what you meant, but I'm going to assume it was, if it's an increasing function, it's always increasing. If it's a decreasing function, it's always decreasing. Let's go back to our tangent function here, the one they drew, that's always increasing between -1 and 1. So therefore, it passes the vertical line test because it's a function. It also passes a horizontal line test in between -pi halves and pi halves. Obviously, it doesn't if you include this portion. So you have to restrict the domain of your of the function definition to make it 1-to-1. You have to stay between -pi halves and pi halves. In this case, it can't be either of those either. Okay, it has to be greater than negative pi halves, less than pi halves, not including because they're not even defined with that. The cotangent would be defined from 0 to pi, but not at 0 and not at pi because it's not defined there either. Oh boy, don't even mess with the secant and cosecant. They get really messy. But you see, this is not one-to-one here, and this one's not one-to-one there. I mean, obviously not. Fails the horizontal line test. So there you have to take this portion of this curve and this portion of the next curve or something weird like that. So we don't usually mess with inverse secants and cosecants. They're messy. Totally messy. Okay. So, continuity of an inverse function if f is continuous on an interval I with a range R, and if f inverse exists, what's required for it to exist? F must be not just a function on that interval, it must be a one-to-one function on that interval, meaning strictly increasing or strictly decreasing on that interval I with that range R. So if f has an inverse, that inverse does exist, then f inverse is continuous with the domain of R. So if the f has a range of R, the f inverse has that as its domain. Because remember, okay, these two, the domain of the exponential function is what? The domain of the exponential function. All real numbers. What's the range of the exponential function? Only positive real numbers, not even 0. Okay? So, its inverse function is the log function. What's its domain? Domain positive, the same as the range of the exponential. That's the domain of this. What's its range of the exponential function, of the log function? All real numbers. Because you see, they flip the domain and range. Just like this was 0.01, this is 0.10. Okay? So you see, every point, its mirror images reflect. That's why we say it's reflected across the identity function. If this was -1, 1/2, just take that one, then this would be 1/2 -1. They flip values, coordinates. So whatever the domain of this one is, that's the range of this one. Whatever the range of this is, that's the domain of this one. Range here, domain here, domain here is the range there. Okay. Does that kind of make sense? Okay. So, I think we beat this to death. Does this make sense? Okay. This section, a lot of blah, blah, blah with very few examples. Okay? We've gone pages now since example 2. Oh my goodness. We've just gone over, haven't we? How time flies when you're having fun. But we're always having fun, right? So y'all better get out of it. Wait. No, I'm wrong. Wrong. I'm thinking my Tuesday, Thursday class. Sorry, we've still got time to go. We go till 10:40. Okay. I was expecting one seat out the door, but he wasn't fast enough. Okay, sorry about that. My Tuesday, Thursday class ends at 9:50, not this one. Okay. Duh. Oh, he's out the door? No, okay. All right. Okay. Okay. Now, let's go to Theorem 5 here. Lots of theorems, lots of blah, blah, blah with very few examples. Sorry about that. Here's Theorem 5. Composite functions. If g is a function that's continuous at x equals c. What does that mean? G is continuous at x equals c. Tell me what that means. G is continuous at x equals c. Means that G is defined on an open interval that includes x equals c. Okay? And that that's the first thing. It has to be defined on some open interval that includes x equals c. The second thing it means is that that f of the g of c, the limit of g of c exists, okay, and is g of c. The limit is g of, as x approaches c of g of x is g of c. Okay. Now f is continuous at some value x, which is g of c. Okay? So g is continuous some x equals c, and f is continuous at some value g of c. Okay? Then the composite function, capital F, which is little f of g of x, is continuous at x equals c. Now, I do not like the fact they call this x. I just do not like it, because this x is not the same as that x. Obviously, that x is x equals c, this x is g of c. I would have named this a y or something other than x, but books today just don't do that. I wish they did, because those two x's are not the same. But here's what they're meaning. You have some value x on some interval, okay? Okay? G is defined and is continuous on that interval that contains that x equals c. Meaning, when you take g of the x in that interval, you get some output. Y, say. Then f evaluated in that y, which is g of c, then that is also, f is continuous there. That means there's an interval there of that y containing that g of c. Then the composite function, which is built of those two, capital F, which is f operating on some g of x is some y value, and f is defined and continuous there, then that function, capital F, is also continuous at x equals c. Okay? I hope you remember composite functions. I don't want to go back and redo those. Any questions about them before we move on? Okay. Now, let me write a couple more things that they skip on the slides, because I know not everybody has books yet. Okay. First, let's do an example of this one. Okay. Here's our capital F function, which is defined as x squared plus 9 raised to the 1/3 power. Okay? Now, that's a composition of what two functions? Okay? When you're given something like this is a review from, hopefully, from pre-calculus algebra. You have an inner function and an outer function. The inner function is your g of x, because that goes inside, and the outer function is your f of x. So in this case, your little f, and they like to call it x, I wouldn't, but they call it x, is equal to x to the 1/3 power, the cube root of x. Okay? The g of x is just the inner function, x squared plus 9. And therefore, this capital F is f of g of x. Okay? In other words, if you start with this one and take the cube root of that, then you get this. Now, that's a composite function. Where is it Where is that function continuous?
X equals C.
Second,
At X equals C.
x equals c. All right, good. And what can c be then?
Integer.
Okay. You first start with your g. Where is this defined? What kind of function is that? Those that we named earlier. Polynomial, rational, power, root, trig, exponential, logarithm. What kind of function is this? Polynomial. It's a polynomial function. Where's polynomial functions defined? And where are they continuous? All real numbers. Exactly. Okay. Now your f function is a cube root function. Where are cube root functions defined? All real numbers. Okay, you got it. If that is square root, only positives. Okay, only positive. Cube root, so because that's your index is odd, all real numbers. So therefore, this is defined for all real numbers. Because any real number x you put in here, well, basically, if this were a square root, no sweat either, because this thing's always positive, right? Your output's always positive for g because you square it and then you add 9 to it. That's always positive. That could have been a square root, and that would have been good for all real numbers. If that would have been a square root, that would have been a minus 9 here. Then you would have had to exclude your g's to be only positive, because you can only take square roots of positive numbers. So this one is continuous everywhere. Okay. How about this one? Alpha of x is equal to cosine of x to the minus 1. Have I got that right? Yeah. Where is that continuous?
Be like real numbers or
Okay, you want all real numbers again? Okay, what does x to the minus 1 mean? Another way you could write that.
X.
Second, whatever x, is that what you said? And that's good for any x? Really?
Well, except 0.
Oh, except 0. Yes, except 0. And therefore, this function can only be, because cosine is good anywhere. Okay, you can evaluate it anywhere, but 1 over x cannot be. It has to exclude x equals 0. So this is continuous. All values x not equal to 0. Okay? You have to do your innermost function first and then restrict the innermost function to values at the outermost function. That one has no restrictions, but the innermost function is still only defined. How about another one? Here's alpha of x is equal to, I just had it and I've lost it. There it is. 2 to the sine x. Where is that continuous, or is it continuous?
Would it be the same as cosine?
Say again?
Would it be the same as cosine on numbers but 0?
Okay. Now, I'm not sure what you mean. First, you tell me what's the inner and the outer function here.
Inner would be 2.
Now, the outer is 2. That's the thing you do last. You first take the sine of x, and then you take whatever that value is, you take that to the exponential. Okay? So, your innermost function is sine x. Where is that defined? Where is that continuous? All real numbers, you called it, okay, all real numbers. And the exponential function, where is it? Because that's what this part is. The outer is the exponential function. Where is it defined? All real numbers. So no matter what the output is here, you can do that. So this is defined everywhere. Yeah. Does that make sense? And it's continuous everywhere, not just defined, continuous everywhere. Okay. Now, can I erase this? It's on the slide. It's not very much there. We just talked about it. Let me talk about another. There's a definition I do not remember them giving in pre-calculus algebra. Maybe where you took it they may have, but they didn't here in the text we were using. Okay? An elementary function. Have any of you ever run into this? What is an elementary function? Anyone know? Have you run into it before? Of course I have, because I've taught other classes, but including this one. But in matrix theory and in linear algebra, you run into elementary functions. So here's what elementary function is. This is a function, obviously, okay, that is constructed I'm going to abbreviate like crazy, out of basic functions. Okay, then we've got to define what basic functions are. Out of basic functions, using the operations of addition, subtraction, multiplication, and division. Okay? Oh, and composition. What's the symbol for composition? Anyone know? We showed it down here that capital F of X is equal to F of G of X, and that's certainly one way to write it. What's the symbol for doing that? Anyone remember that? Capital F of X would be little f composed with G of X. This means that. Okay. So I was starting to write down the center zero, but I wasn't sure you'd know what I meant. That's the symbol for composition of two functions. So an elementary function is a function constructed out of basic functions using the operation of addition, subtraction, multiplication, division, and composition. And basically, we've just done them. Okay. Since the basic functions are continuous on their domains, and what are the basic functions? Okay, if you go back a few slides, continuity of some basic functions. Well, we had already hit polynomial and rational. Those are basic functions. Then other basic functions are your basically root functions. That's what that stands for. Your sine and cosine functions. And it's funny they don't include the other trig functions. I think they're also basic functions, but don't hold me to that. Your exponential functions and your log functions. Okay? Now this includes the e function and the natural log, but all exponential log function. Those are your basic functions. Okay? So then what where is it? There it is. An elementary function is a function that is constructed out of the basic functions, polynomials, rationals, sines and cosines, root functions, and exponential log functions. Using the operations of addition, subtraction, multiplication, division, and composition. Okay. Since the basic functions are continuous on their domains, remember that little caveat's there, elementary function is also continuous on its domain by the laws of continuity, which we've just been doing. Here's an example of an elementary function. I think I'm going to clear this slide just because it's already got so much on it. Okay, y'all got it? Here's an example. F of x is equal to the inverse tangent, of x squared plus cosine of 2 to the x plus 9 divided by x minus 8. Okay. My word. Okay. This as I said, when I mentioned sines and cosines, tangents and tangents and cotangents also were there. I just didn't know whether they included secants or cosecants. I'd rather not, but they may. Okay. Now remember also we said the inverse functions are continuous functions. So since tangent is a basic function, inverse tangent is a basic function. But this is a composite of that with that numerator. So that's a polynomial function, a cosine function, an exponential function, and an addition function. All those being basic functions, and these operations adding, all these things are good. Division is also an acceptable operation, and the denominator is a polynomial function, but you're restricted because it is a division. This cannot be 0. So this is good everywhere except x equals 8. Okay? That you can't have. You can have any value here, any value here, any value here, any value there, and any value there. Now, they're assuming you remember your inverse trig functions. Okay? If this had been an inverse sine or cosine, you're restricted. The thing that's in there has to be between, for a sine, between minus pi halves and pi halves, including. Cosine between 0 and pi, inclusive. Tangent, even though a tangent function is limited between minus pi halves and pi halves, the inverse tangent function, because it's the inverse of that, tangent function ranges all real numbers. So therefore the inverse tangent has a domain of all real numbers. They kind of snuck that in on you without explaining it, but indeed that's true. That's defined for every x not equal to 8. All right. Now, strange but true, what I've already been telling you can do, they're now telling you can do. And that is substitution, evaluating the limits using continuity. As long as it's within, as the function is defined there, you can just plug it in. And that's called the substitution method. Now, that's coming up later, so I'm not going to go to that slide. Okay? Basically the same thing we've already been doing. So let's just continue doing it. Okay? Example 3, evaluate this. The limit as y approaches pi thirds of sine of y. Anyone want to hazard a guess what that limit may be? Second? I can't hear. Not 0. Sine is 0 at 0, pi, 2 pi, 3 pi. All your multiples of pi. Pi thirds is not a multiple of pi. Second? Square root of 3 over 2. Bingo. Or I can't say that in Alabama. Yeah, the square root of 3 over 2. Okay. Absolutely right. Because, guess what? Sine is a continuous function. It's a continuous function, so there's no gaps, holes, or anything else. So you just plug it in. Okay? That's what allows you to do that. Okay, that was so easy. Let's try another. The limit as x approaches -1 of 3 to the, I can't write, say it right but write it wrong, 3 to the x divided by the square root of x plus 5. All right. What about that?
Six.
1/6. Excellent. Okay, how did you get that?
So 3 to the power of -1 would be
1 over 3.
the square root of -1 minus plus 5 is 4, which equals 2.
Right.
So we do that there over 2, and then
Yeah. Right. You got it. 1/6. Perfect. Perfect. Now, for some reason, these books, just about every math book, loves the greatest integer function. And I guess there's a reason for them to love it. I haven't figured out what it is yet. But here is what the greatest integer function is. I'm going to show it here. This is a graph of it. Let me write, sorry. The greatest integer function, which is defined as this. Now, in some math books, you'll see a double bracket here. Okay? That's how they do it. This book just uses a single bracket. So be careful for that. If you're used to seeing the other way, just don't get confused. Same meaning, just different notation. Okay? The greatest integer function is the function defined by this equal n, okay, where n is the unique integer okay, such that, and this is a symbol for such that, sort of a colon looking thing there, n is less than less than or equal to x is less than or equal to n plus 1. Okay? That's a rather strange way to do it, but it's exactly stated correctly. Where n is a unique integer such that n is less than or equal to x and x is less than or equal to n plus 1. The way I usually hear it said is the greatest integer in x, okay? Less than or equal to x. So basically the first part there, okay? Second part is still true, okay? So let's just take an example here. I think they give us one here. What is the greatest integer in 4.7? Anyone give me a hint? Greatest integer in 4.7. The largest integer that is less than or equal to 4.7. Second? 4. Exactly. In other words, for positive decimals or fractions, lose the decimal. Lose the fraction, that's the greatest integer. That's for positive numbers. What would be the greatest integer in negative 4.7? Second? I said you can do that for pauses, -5, because it has to be the largest integer less than or equal. Less than or equal means to the left of, right? And -4 is to the right of -4.7. So you have to be -5. Okay. Good deal. Okay. Now, here's the graph. Okay. Greatest integer less than or equal to 0 is 0. And less than or equal to 1/2 is 0. 7/8, 0. You know, right, left, okay. Up to 1, but when you get to 1, you jump up here because 1 is less than or equal to 1. So you jump up. So this is what they call a step function. The closed circle on this side, the open circle on that side. Okay? What kind of function is what? Is this a continuous or not function? Continuous or discontinuous? I hope it's obvious. This is a discontinuous function like crazy. What kind of discontinuous function? Remember the various kinds it could be? Is what? Jump. This is a jump discontinuity. At every phase of the way is a jump discontinuity. What are the other types of discontinuous function? Say again? I can't hear. Okay. This could be defined. You define a function whether it's piecewise or not. But the discontinuities can either be removable, jump, infinite, or none of the above. Okay? This is a jump discontinuity. Big time. Every step is a jump. Okay. Okay. So let's do example 4. Can we evaluate the limit as x approaches 2 of greatest integer in x using substitution? Most of the time we like to just plug it in. That's what we mean by substitution. And that might be your first inclination here. But you have to remember the caveat. You have to remember the given. In order to use the substitution method, if you look right above the thing, oh boy, it's not it. It's easy to evaluate a limit when the function in question is known to be continuous, especially at the value in question. Is that continuous at x equal 2? No, that's one of the jumps. So you can't use substitution method for that one because it's not continuous at x equal 2. It would be continuous at x equal 2.1 or 2.7 or 2 and 17/16. You know, any of those values, yes, it's continuous there. So yeah, you could plug it in, and you get the right answer, but not at the point of the jump. That would be here. At x equal 2, you have the jump discontinuity. You cannot substitute at a discontinuity. Okay? Ever. Okay. Now, there's a little conceptual insight here, real-world modeling of discontinuous functions. I think they're going to show a graph here, okay? This is a little on the jagged side, and that's because we don't have great data here. But if you look at the temperature, they're given in degrees Celsius, when you're at various altitudes, okay? Generally here on the surface of the Earth, if you go up in altitude, what happens to your temperature? What do you see on the top of the tallest mountains? Typically. cold enough, yeah, I mean, it is. Now, not that, well, you'll still see it sometimes in the year. Mount Kilimanjaro. Anyone ever heard of it? Okay, anyone know where it is? Second? Africa, for sure. Actually, most of it is in Tanzania, but it almost is on the border with Kenya. So both of them kind of claim it, but not quite. It really is in Tanzania. Very famous American writer, Ernest Hemingway, wrote a book, a novel, short novel, I think it was. Anyone remember the name? Had to do with Kilimanjaro? The Snows of Kilimanjaro was the name of the book. Because Kilimanjaro used to have a glacier on it. Okay? Now, at certain times of the year, it may still have snow, but that no longer year-round. Okay? He wrote it back when it did, but because, even though some people say it's not happening, global warming, well, I think most people agree it is happening. It's just whether it's man-caused or not. But it is happening. Global warming does seem to be, because Hemingway wrote back in the 1930s, there is no snow on Mount Kilimanjaro, not year-round anymore. Maybe occasionally at certain seasons you might see a little bit. It just doesn't snow there. Things have warmed up enough that it doesn't. But as you go up the mountain, and by the way, where is Mount Kilimanjaro? It's in Africa, Tanzania, Kenya. It's right on the equator. And yet it has snow at high elevation. Right on the equator is usually the hottest year-round. But Mount Kilimanjaro used to have snow. So yeah, if you go up in altitude, your temperature drops. Below 0 on the Celsius scale is the freezing point of water. Okay? So yeah, anywhere below that, you're going to have snow or ice on that mountain. Okay? So as you go up, the temperature drops. Any of you ever ridden in a jet plane? I assume some of you have, right? Have you ever watched, especially, okay, I'm sorry, I should have rephrased that, traveled intercontinentally on a jet plane? Usually they'll show several features, wind speed, blah, 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 and temperature outside. If you ever looked at those temperatures when you're way up there, very, very cold. Very, very cold. So the higher you go, the temperature decreases. There you're in what they call the troposphere, anywhere it looks like 0 to 10 kilometers in altitude. I don't know if many mountains are below or beyond 10 kilometers. It looks like about 12 here or something like that. That's pretty tall. They keep going up. I think all the mountains are less than that. So you keep going up. And at some point there in the stratosphere, the temperature levels off, very cold still, very, very cold, but it levels off, and then at some point it starts increasing again and actually typically gets above freezing again. And then when you get into the mesosphere, which is about 50-some kilometers up there, way, way up there, it starts dropping again to extraordinarily cold temperatures until you get into the thermosphere, and then, look at that, it goes extraordinarily hot, okay? Now, the way they've drawn it, is that a continuous function or not? Yeah, it sure does look continuous. Do you think they just drew it that way, or would it have to be? I cannot imagine going up in atmosphere, in altitude, and you be at some temperature, and suddenly you jump to another temperature. It doesn't happen that way. Temperature on the thermometer outside, no matter how hot or cold it gets there gradually. You don't have any gaps. Neither do you in altitude. That is, by definition, and I should have blown it up, a continuous function. I can't get them both on there, but I can get one. Okay? That is, by definition, a continuous function. It's not just that they've approximated. It has to be. Your temperature can't suddenly go from one temperature to another just because you went up another inch or millimeter or something. You can't do it. It goes up gradually. There's no jumps in it. Okay? How about this one? World population in millions. You think that's a continuous function? To within an integer. Okay, you don't have any half people in there, okay, or 3/4 person. But within integers, yeah, it's continuous. Yeah. Reality, they don't actually show that. You can't show in millions, yeah, it would be continuous. But if you had individual people, there would be, this would only be integers here. But it's still a continuous graph because every point here corresponds to a point there, you know. So this is reality, folks, too. And guess what? Doesn't seem to be leveling off too much either. Maybe going up at a little bit slightly less of an angle. Why do you reckon it took off like this? That was back in the early 1900s and the later 1900s. Why did the population take off like that? Two primary reasons, I think, and maybe others. Anyone think? This doesn't have anything to do with calculus, I'm just wondering. Number one, we kind of got diseases figured out. So most of the world's population, not all, but most of it has access to antibiotics, vaccinations, and stuff. Certainly some parts of very, like last year or a few years ago, Zika broke out in Liberia, wasn't it? And Sierra Leone and some of those countries. We didn't have good, but we still got them, you know, the medications there. It was pretty bad for a while, but they got them back under control. Ebola, I said Zika. Ebola, okay? Zika has broken out in other places, but usually it doesn't. It does cause some deaths, but not massive like the plagues and stuff like that, okay? That's one. What's the other? Okay, technology in what sense? Okay, I think we've cut out most, not all, but most major famines because we now have the technology to grow enough food to feed who we got so far. Can it continue like that? I don't think so. Okay, I don't think foreseeably we can come up with enough new technologies to continue producing food, especially if our population keeps growing and needs more space to have people living and less space to raise crops. Someplace there you're going to run into a problem. Pretty big problem. So, yeah. But that is pretty much, the graph looks continuous, though you realize it only goes up a person at a time, no fractions of people. Okay, let's see if we can get the preliminary questions. Summary there, again, this is a lot more blah, 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 only 4 examples in the whole section, but lots of theorems. What was it, 6 theorems? 5 theorems. Okay, so more theorems than examples. Let's look at the preliminary questions. Okay, I think what I'll do, I think that, yeah. What's that? And that's all, I know. Okay. Hit this one. Okay. This. Okay. Let's hit as many of these as I can. Which property of f of x is equal to x cubed allows us to conclude that the limit as x approaches 2 of x cubed is equal to 8. Okay, it's which property? What's that?
Substitution.
Okay, yeah. It fits the substitution thing because this is a continuous function. So continuity is probably what they're looking for here. We'll check and see. Continuity allows you to substitute. X is continuous at 2, so the function x cubed is continuous at 2, the cubic function continuous at 2, therefore you can plug it in. This is, yeah, they're looking for continuity, okay? But yeah, allows you to do substitution. Okay, number 2. What can be said about f of 3 if f is continuous and the limit as x approaches 3 of f of x is equal to 1/2. So what can be said about f of 3 if f is continuous and the limit as x approaches 3 of f of x is equal to 1/2? Don't try to make it any harder than it is. Because f is continuous, you can use substitution. If you use substitution, what does this tell you? F of 3 equal 1/2. So therefore, f of 3 is equal to 1/2. Basically, it's probably so obvious you'd never think of it. Okay, so that's what they're doing. So I think that's what they're saying. Yeah, I looked at f. The previous section, it was a different answer. I said, it can't be that. There's no way it can be that. I was looking at the wrong thing. Okay, number 3. Suppose that f of x is less than 0. Okay, if x is greater than 0. Okay, and f of x is greater than 1 if x is negative. Can f be continuous at 0? What do you think? No. You're absolutely right. If f is always less than 0 for every value of x greater than 1, that means it's always going to be down here. And if f of x is always greater than 1 at every value over here, there's no way it can be continuous at 0. Because the limit as x approaches 0 from the left-hand side can't be greater than 1. I mean, can't be less than 1. It could be 1, but it can't be less than 1. And as it approaches from this side, it has to be less than 0. No way. Does everybody see that? The answer here is no. Okay. I think we're out of time. Now, do you want to continue those last few before when we start next time, or can you do those at home? You don't have books yet. Okay, you think it? Okay. So you want to continue those, pick up there next time? So we did 1 through 3. Are these worth doing, or you want to go on to the next section? You tell me. Want to start in 2.5 or finish these last 2 preliminary questions? Okay, we'll start at 2.5. Homework exercise in 2.4. Let me get those done then. Do number 1. Do number 3. Do number 5. Then do any of the odds 7 through 15. Any of the odds 17 to 33. Any of the odds 35 to 47. Do 49, that's a piecewise defined function. Do either 51 or 53 or both. do 55, either 57 or 59 or both. Do 61, do either 63 or 65 or both. Then do any of the odds 67 to 79, and then do either 81 or 83. You can look at further insights and challenges, up to you. We will do 2.5, start with that next time. Good deal. Any questions?